Section 1.1, displaying distributions with graphs. Some things we will look for anytime you are asked to examine a distribution. First thing, you will look for the overall pattern and any striking deviation from that pattern. You can describe the overall pattern of a distribution by its shape, center, and spread. And in this first section, we're not going to get into great detail in these three things. In section 1.2, we will know which measures of center and which measures of spread exactly that you should use depending on the shape of the distribution. An important kind of deviation is an outlier, which is simply an individual value that falls outside the overall pattern. This acronym SOCS, S-O-C-S, anytime from here on out on a quiz or a test, and especially the AP exam, that you are asked to describe a distribution, examine this distribution, compare these two distributions, think of this SOCS acronym, and make sure you talk about each one of the four letters in the acronym. Shape, outliers, center, and spread. Comment on each one of those four anytime you are asked to describe a distribution. Does the distribution have one or several major peaks called modes? If it has one major peak, it is called unimodal, two major peaks, bimodal, and so on. A distribution is symmetric if the values smaller and larger than the midpoint are mirror images of each other. It is skewed if the right tail or left tail is larger than the other. So when you describe shape of a distribution, you only have one of three choices. You will say it is approximately symmetric, you will say it is skew right, or it is skew left. That is it. So when you're describing a distribution and you use the SOCS acronym and you are going to discuss shape, you will say the shape is approximately symmetric, skew left, or skew right. One of those three things are your only choices. So when we talk about skewness, looking at this first graph here, this first graph is an example of a symmetric distribution. If we look more closely at statistics from this data set, if it were perfectly symmetric, that would tell us that the mean, the median, and the mode are all equal. Distribution down here on the left is skew left. Sometimes in other textbooks you will see that called negative skewness. You just need to know skew to the left for this class. And an important feature of a skew left distribution, notice that the skewness is based on the long tail, not where the peak is. This peak is on the right. It is not a skew right distribution though. Skewness is in the direction of the long tail. And as far as the summary statistics go, the important feature of a symmetric or of a skew left distribution is that the mean is always pulled in the direction of skewness. Specifically, the mean will always be less than the median if you have a skew left distribution. Remember that feature. On the right is a skew right distribution. Other textbooks may be talked about in terms of positive skewness. Again, you do not need to know that necessarily for this class, but know that if you take additional statistics classes, you may see it referred to that way. Notice the long tail is to the right. That's why it is skew right. And just as in the skew left distribution, the mean is pulled in the direction of skewness, and the mean will always be greater than the median for a skew right distribution. Notice the mode in all three distributions is always the peak. That's the value that appears most often. Okay, we talked about categorical variables, those variables that we measure that place something in a certain category. We have a couple of different graphs that we can use for categorical variables, bar graphs and pie charts. This data set here is the radio audience rating service Arbitron places the country's 13,838 radio stations into categories that describe the kind of programs they broadcast. Here's the distribution of station formats. So we have all the different categories that we can place the radio stations in. We have the total count of radio stations that fall within each category, and we have the percent of stations here on the right. Notice our percent does not add up to 100%, but our total count of stations, 13,838, is the total in the country. The reason for that is because we have rounding error here. Anytime you have a data set and items have been rounded, there could be rounding errors present. It doesn't change anything. It doesn't mean it's wrong. It just means here that these percents have all been rounded only to the 10th position, and therefore there was a rounding error of 1/10 to make up that 100%. Okay, so two things we could do here. We could do a pie chart, which is done on the left here. You will not have to construct pie charts on your own. Okay, pie charts are nice if you have a computer program that you are going to use. Okay, but for us, anytime you have a categorical variable, you are usually going to use a bar graph. A pie chart is used only when you want to emphasize each category's relation to the whole. So a pie chart, we can quickly look and see what part of the whole is represented in each piece of the pie. For bar graphs are easier to make, and you are going to want to use them instead of pie charts. Again, the bottom cut off here, the only words you're missing, use them instead of pie charts. For quantitative variables, few different graphs that we can use for quantitative variables. Stem plot is one. Stem plot is sometimes referred to as a stem and leaf plot, and it's a quick picture of the shape of a distribution. To construct a stem plot, number one, you're going to separate each observation into a stem consisting of all the digits but the final one, and a leaf consisting of the final digit. Write the stems in a vertical column with the smallest digit at the top and a vertical line to the right of the column. Last step, write each leaf to the right of the stem in increasing order. And we'll look at the construction of a stem plot here later on. Back-to-back stem and leaf plots are useful for comparing two related distributions. So pretend that we are asking a question about the attendance policy at our school, and we are recording responses in a sample of students. Well, if we want to separate those students by male or female, we could do a back-to-back stem plot, which then we could get a good picture of if there is a difference in how male students feel towards the attendance policy versus female students. Something else that may be necessary when doing any type of stem plot is splitting the stems. For a large number of values, we're going to split each stem with one containing the leaves 0 through 4 and the other containing the leaves 5 through 9. So if we're talking about ages, okay, 10 through 20 represented here. Our stem would be the 1, and then our leaves of 0 through 4 would represent ages 10 through 14. Our stems of 5 through 9 would represent ages 15 through 19, okay? And if we have a bunch of people in that age group of 10 through 19, we're going to want to split those stems so we can get a better picture of the overall shape of the distribution. All right, looking at our first example here. Tuitions and fees. For the 2005-2006 school year for 62 and 4-year school colleges and universities in Virginia are shown. And the stem plot shows that they ranged from a low of 2135 for the 2-year community colleges to a high of 34,850 for the University of Richmond. Okay, on the right here is your mini-tab output for this data. You will have to read computer output in this class. Okay, a couple of important features here is it tells us that the leaf unit for this data is to the thousands place, which means that all of these dollar amounts off to the left here have been rounded to the nearest thousand of dollars. Okay, so here's our stems going down here. Here are our leaves over on the side. So all of these on the right here, this represents a school that costs, Here's our most expensive one down here at the bottom at $34,000, which was $34,850. So notice what has been done here is the hundreds dollars have just been truncated. They've just been cut off. So there's no rounding going on here. Okay, so this 2 and 5 right here represents a school that costs $25,000 and so on. So each of these up here in the top row, 0 in the $10,000 position, all of these schools cost $2,000. Also in the STEM plot here, notice that these counts going in this column right here. What that is a cumulative count from the top going down and a cumulative count from the bottom going up. So as I look at the bottom here, I have a 1 next to this first area here because there's one school that costs in that dollar range. As we're going up, it stays at 1 until I get to here because that's the next school that we have that falls in our STEM plot. Then we add 5 more schools for a total of 7. We add 4 more schools here for a total of 11, and so on. And it's doing the same thing as we count from the bottom or from the top. And then you will have in a mini tab output one with parentheses around it. That is identifying the center of the data by the median. So we know the median occurs somewhere in this row of values in our stem and leaf plot. Looking at our first question here. Which stem and leaf represent Liberty University? Which stem and leaf represent Virginia State University? And identify the colleges represented in row 2 with the 4 ones. So the first thing, for Liberty, we need to identify the stem and the leaf. And for Virginia State, we need to identify the stem and the leaf. Well, let's look for Liberty first. If you go in alphabetical order here, there's Liberty University. Costs $13,150. Remember, we are truncating or getting rid of the hundreds. So really, we're looking at $13,000. So $13,000 would be represented by a stem of 1 and a leaf of 3. Virginia State. Virginia State is right here. Truncate the hundreds. So it costs $11,000 based on this stem and leaf plot. So it's a stem of 1 and a leaf of 1. Third part to this question, identify the colleges represented in row 2. Well, those schools in row 2 are all the schools that cost, talking about this row right here. So all the schools that cost $21,000. So let's look for each of those individually. There's one there that costs $21,000. There's one there that costs $21,000. There's one there that costs $21,000. And the bottom one you can't see here on your screen, but you should have it on your paper. So there are 4 schools that cost $21,000, which we knew because there were 4 schools in that row. They are Hollins, Randolph-Macon Women's College, Sweetbriar, and William and Mary. Letter B. There's a string of 23 twos at the top of the stem plot. Which colleges do these numbers refer to? The stem for these entries is 0. What range of numbers would be plotted with this stem? Okay, so the first of all, those are all of the 2-year or community colleges. So those 23 twos represent the 23 community colleges in Virginia. range of values that would be plotted within that stem are all schools costing between, and now what dollar ranges are represented here? Well, it looks like each stem, if we look down further, 1, 2, 3, 4, 5 ones, 1, 2, 3, 4, 5 twos. So those are going to be all schools that cost between $2,100 and $2,300. So each stem we're dividing by 5, so that would be all in the first stem, which isn't written there, would be all the schools that cost. I'm sorry, I wrote this wrong. This should be between 2,200 and 2,400. So our first stems would be all those costing 2,000 or 2,100. Next stem 2,200 or 2,300, which is the one that we are talking about here. Exercise 1.6. A marketing consultant observed 50 consecutive shoppers at a supermarket. One variable of interest was how much each shopper spent in the store. Here are the data in dollars. Round each dollar amount to the nearest dollar, then make a stem plot using tens of dollars as the stems and dollars as the leaves. So this time we are going to truncate or get rid of all of our cents here. So we're only talking about whole dollars. So our stems are simply going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 down the side. Our leaves then are going to be, well, in our first stem section of a tens digit of 0 would be all those under $10. So I have leaves of 3, 9, and 9. Let's go ahead and round here. Let's not truncate. For our $10 amounts, so that's anything in the teens, we have 1, 3, 4, 5, 6, 7, 7, 8, 8, and 9. In the $20 amounts, we have 0, 0, 0, 1, 2, 3, 4, 5, 5, 6, 6, 8, 8, 8. So we have a bunch of them in there. $30 amounts, 32, 5, 6, 9, and 9. $40 amounts, 1, 3, 4, 5, 5, 7, 9. $50 amounts are 50, 53, 55, 59, 61, 70, 83, 86, 86, and 93. Okay, with a stem plot. And it's kind of cut off here, but again, you should see it on your note sheet. The key is the key. If you don't have a key, it doesn't tell people how to read your stem plot. You can pick any value you want out of the stem plot. It doesn't matter. If I pick the 3 as my stem, the 2 as my leaf, you need to write it just like that with the line representing the separation between the stem and the leaf. And then what does that represent? That represents $32 that were spent, and now that should be enough information for the people to read the rest of your stem plot. Because we have a lot of leaves in the $10 range and $20 range, you may or may not want to split leaves here. We're going to look at what it would look like just so you can see how to split leaves, or to split stems, I'm sorry. Means we're going to split each one in half. So this time I'm going to have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, and 9, 9. And now for my leaves, for my first stem of 0, I'm going to have between 0 and $5. For my next one, between $5 and $10, and so on. So I'm going to have the 3 here, and the 9 and the 9 here. So in other words, anything 0 through 4 is a leaf, is going to go in the first column for each stem. Anything 5 through 9 is going to go in the second column. So go ahead and fill out that leaf plot now. Okay, so there, and again, make sure you have your key down here at the bottom. Does not matter which stem and leaf you choose for your key. Now the question is, which of the plots shows the shape of the distribution better? Well, if I look back at the first one, okay, we can see that we're going to have a high peak here on the left if you think about turning this, and a long tail to come catch these values on the right. So we can see there pretty clearly that it is skew right. From our split stem plot, we can basically see the same thing. So in this case, it probably wouldn't have been necessary to split stems. Just wanted to show you an example of splitting. Okay, so again, in this case, both stem plots show a skew right distribution. Write a few sentences describing the amount of money spent by shoppers at the supermarket. Okay, so we're asked to describe this distribution. Again, notice this doesn't say talk about the shape, center, outliers, and spread of the distribution. It just says describe it. Anytime you are asked to describe a distribution, though, talk about each of those 4 things from your SOX acronym. So we already talked about shape. Shape of the distribution is skew right. The spread. Section 1.2 will get more detailed in spread. For right now, the simplest and only measure of spread that you have probably learned in other math classes is the range. Range, remember, is simply a single value for the highest minus the smallest. So the range is $90. And again, the way we got that was taking the 93 minus $3. Center. We don't want to have to add all these up, so let's identify the center by the median, which is the middle number. Well, how many shoppers did we have here? We were told that we have 50 shoppers, so if I count in 25 shoppers from each side. 25 shoppers from the top puts me at that shopper right there. Count 25 shoppers from the bottom puts me at that shopper right there. So both of those are shoppers that spent $28. The number in between this 28 and that 28 is 28. So the median is going to be $28. Finally, outliers. If we look at our split stem plot, we see that these values, there starts being gaps in here and then only single values. So any of these values in here could be potential outliers. So we can just say in general terms that there may be some outliers and tell where they are. In this case, there may be some outliers at higher dollar amounts spent. Histograms. For a histogram, you're going to choose a class width that is equal for all classes and divides the data up so that the histogram is not too tall or too short. Pretty general. In other words, there isn't a right or wrong answer. Okay, choose a class width that's easy to work with. So in other words, if you're talking about a data set that goes from 0 up to 500, okay, probably dividing up into 5 classes may not be enough. Typically 8 to 10 classes are kind of a ballpark number that you may want. But again, there is no right or wrong answer. Choose enough so that it sufficiently spreads out the data and it's easy to work with. So if we're talking about 0 to 500, we may go 0 to 49, 50 to 99, 100 to 149, 150 to 199, and so on. Choose something that's easy and quick to work with, but sufficiently divides up the data. Then you're going to make a frequency table with the classes and the frequencies within each class. So you're simply going to do a tally then within each one of those classes of how many data points fall within each class. From there, you're going to use the frequency table to construct the histogram. We'll look at the construction of one of these histograms here in one of the next examples. Okay, looking at a histogram here. Here's a histogram showing the distribution of the number of frost days during April in Greenwich, England over a 65-year period. So we have 65 years worth of data, one for each year represented here. And we're counting the number of times or the number of days in the month of April in which the temperature fell below freezing. Okay, so in 15 of those 65 years, it never fell below freezing. In about 11 of those 65 years, there was one day in which it fell below freezing, and so on. If we go all the way out here, looks like about 2 days, or 2 times out of the 65 years, there were 10 days below freezing. First question, describe the shape, center, and spread of the distribution. Are there any outliers? So again, we see our SOX acronym here. If we look at the overall shape of this distribution, and again, if you just think about drawing a smooth curve over this distribution, it would look something like that. We can clearly see that we have a long tail on the right side. So the shape of this distribution is skew right once again. Center of this data set. Well, the center, if we 65, the middle value is going to be 32 years. So we need to count up where we have 32 years. We have 15 years represented in this column. We have 11 represented in this column. 5 represented in this column. So that's 26, that's 31, which means our 32nd one is going to fall somewhere in there, in which 3 days of frost happened in April. So again, we're talking about median. Which is 3 days of frost. Also, when you're talking about these, talk in the context of the problem. Don't just say the center or median is 3. 3 what? 3 months? 3 days? 3 years? In this case, the center or median is 3 days of frost in April. Spread. Right now, the only measure of spread that we're going to talk about is range. Section 1, 2 will get into the better ways of explaining spread. In this case, the spread is going to be 10 days. Finally, outliers. There's really no gaps in the data. I suppose you could say that, but again, since this happened twice, maybe not, but you could say, I suppose, that there are some potential outliers. But I would say for the most part, since there are no gaps in the data, that there probably are not any outliers. In what percent of these 65 days did the temperature never fall below freezing? Well, if we look at our chart, it never fell below freezing 15 times out of the 65 years. If we round that, that's approximately 23%. Okay, this histogram shows the distributions of the lengths of words used in Shakespeare's plays. Describe the shape, center, and spread of the distribution. So again, they're telling you specifically the three things. On a test quiz, you probably won't see that. It will probably just say describe the distribution. You need to know to use your SOX acronym. Once again, what is the shape of this distribution? Well, if I attempt to draw a curve through this distribution, we can pretty well see again that this distribution is going to be skew to the right. Center, again, if we look at median, notice this is percent. So we know it's between 0 and 100. Where's the median going to occur? In the 50th percentile. So again, I'm going to go through and I'm going to add up. This is approximately 5%. Here we have approximately, let's say, 18%. Here we have approximately 22%. So there's 45, which means somewhere in here is going to be our median. So the center, which again we are measuring by the median, in the context is 4 letters per word. Finally, the spread. Well, 12 letters were the most. 1 letter is the fewest. Subtract those. It's 11 letters. Some general rules for any graphs. Okay, you're going to have a bunch of different graphs that you're going to have to be able to identify. You're going to have to construct one on the first free response question of the AP exam, more than likely. Some general rules that are always safe to go by. Always title the graph. Let the reader know what it is you are displaying in your graph. Always label both axes, including units. Spread out the vertical and horizontal axis in equal increments. If you're given a grid, try filling up the majority of the grid with your data set. Use percentages for the vertical axis whenever possible, especially if you're comparing two data sets. Okay, it's not bad to use just counts. Sometimes counts, because they can have such a large range, makes it a little bit more difficult. Okay, and then you'll want to use percents. And anytime you are comparing two data sets, make sure you always use percents, because that converts everything to equal scales in case we don't have equal counts in both data sets. Relative frequency and cumulative frequency are shown in an ogive. An ogive is simply a relative cumulative frequency graph. Takes a little bit of time to set up the information you need in order to construct an ogive. First thing you're going to do is you're going to make a chart with 5 columns. Class interval and frequency. Notice those first two are the same ones that you have to do for a histogram. Okay, now if it's going to be an ogive, you got to add 3 more. A relative frequency, a cumulative frequency, and a relative cumulative frequency. From there, once you have that, that's all the information you're going to need to be able to draw your graph. Then follow your other general rules. Label and scale your axes, title your graph. Okay, and this is the key. Plot a point corresponding to the relative cumulative frequency in each class interval at the left endpoint of the next class interval. And this last part is exactly what you're also going to do when you have a histogram. So we go to the next class, we take that left endpoint, and that is what we are going to label along our horizontal axis. Okay, overall then, an ogive is going to look a lot like a line graph. So you're going to have points, you're going to connect those points with line segments, and that's how you are going to create your ogive. So looking at this data set, people with diabetes must monitor and control their blood glucose level. The goal is to maintain fasting plasma glucose between about 90 and 130 milligrams per deciliter of blood. Here are the fasting plasma glucose levels for 18 diabetics enrolled in a diabetes control class, 5 months after the end of the class. How well is the group as a whole achieving the goal for controlling glucose levels? So we don't even need a graph here to answer this. We know our target is to be between 90 and 130. Well, between 90 and 130, there's 1, 2, 3, and 4. So only 4 out of the 18, or approximately 22%, achieve the goal. So how would you say that they are doing? Not very good, because 22% of the patients were in the target zone. So they are not doing a good job. Construct a relative cumulative frequency graph or ogive for these data. So again, we're going to need 5 columns. We need whatever class we're going to pick out. We need a frequency column. If we were doing a histogram, that would be all we need is class and frequency columns. But we're not, so we need a relative frequency. We need a cumulative frequency. And we need a relative cumulative frequency. Most important thing is, how do we pick our class width? Well, again, there is no right or wrong answer. Usually you approximately want 7, 8, 9, maybe up to 10 classes. In this case, our low is 78. Our high is 359. So that's about a span of 300. Let's divide that up and let's go by 50s. And again, go by 50s in a way that is easy for you to pick the classes. So let's go 51 to 100. 101 to 150, 151 to 200, 201 to 250, 251 to 300, 301 to 350, and 351 to 400. Go through and count how many end up in each one of those classes. There are 3 in there, 7 from 101 to 150, 5 of them from 151 to 200, none in the next group, 2 of them in here, none in the next group, and 1 in there. So now for our relative frequency. Go through and divide however many there are, divided by the total. So for the first group, we're going to go 3 divided by 18, which is 16.7%. Next group, 38.9%. Next group, 27.8%. 0%, 11.1%, 0%, and 5.6%. Cumulative frequency simply takes our frequencies and adds them up as we go down. So our cumulative frequency up through the first class is 3. Second class, we add 7 more, so it's going to be 10. Third class, we add 5 more, so our cumulative frequency through the third class is 15. Fourth class, we don't add any. Next class, we add 2, don't add any, and add 1 for a total of 18. So your cumulative frequency column should end up with the total number represented in your data set. And now relative cumulative frequency is going to be the same thing now with our relative frequencies. So through the first class is 16.7% of the data points. Through our second one, 55.6% of the data points. Up through our next 83.4%. Up through our next one is going to be 94.5%. And finally, adding the last one in is going to take us up to our 100%. That now is going to allow us to construct our ogive here on the next slide. So anytime we have an ogive, what we are measuring, remember, is a relative cumulative frequency. How are we measuring that? In a percent. Again, include units if you can. Along the bottom here, we are measuring glucose levels. Units are milligrams per deciliter. So up the side is going to be percents. Again, spread out your graph as best you can. Along the bottom, this is the key. We need our left point of the previous class interval. So we're going to start here at 50. 100, 150, 200, 250, 300, 350, and 400. Plot your points between 0 and 50, which is this first interval. We have 0%. Next interval takes us to 16.7%. Next interval, up to 55.6%. Next one to 83.4%. Stays there. Jumps up to 94.5. Stays there. And finally the last one, which always then should be our 100%. Connect those with line segments. And there is our ogive. Okay, if we do the same thing with the histogram, remember for a histogram though, all we would need are these first two columns, class and frequency. So let's go ahead and do a histogram of the same data. Okay, for a histogram, again, all we are doing is frequency and class width. So up the left side here is going to be frequency. And if we look back at our frequencies here, they go up to 7. So to spread our data out so we get a clear picture, let's go every other one here. So 1, 2, 3, 4, 5, 6, 7, and so on. Down along the bottom is still going to be our glucose level. In milligrams per deciliter. Still going to have the left points and now we're simply going to do bars representing. So between 0 and 50 there was nothing. Between 50 and 100 our bar would go up to 3. Between 100 and 150 go up to 7. Next group back down to 5. Down to 0. Back up to 2. Down to 0. And the last group here, back up to 1. And that would represent our histogram. Okay, use your graph from part B, so the ogive, to answer the following questions. What percent of blood glucose levels were between 90 and 130? Okay, so we know directly from our data set that it's 22%. But if we were just given the ogive, we want to know between 90 and 130. Well, 130 is going to be, this is 125, so just past this line here, so somewhere in here, it's about 130. 90 is going to be just before the 100. So about right here, which is at about 15. 90, if we trace that over, is about at, let's say, 38. So we would go 38 minus 15. Let's call this part A. So what percent is between 90 and 130? Well, 38 minus 15 is about 23%. So we can see from the ogive we can get that same information pretty easily. What is the center of the distribution? Should be easy to get from the ogive. Center, remember, is going to be at the 50th percentile. 50th percentile is right here. Trace that down. Just less than 150, call it whatever you want. Somewhere between 125 and 150, but closer to 150. Let's call it about 140. What relative cumulative frequency is associated with a glucose level of 130? Well, 130 is going to be right here, and we said that that was about 38%. So about 38% of the data is 130 or less. Time plot. Plots each observation versus the time it was measured. Always put time on the horizontal scale and the variable you're measuring on the vertical scale. A time plot is really just a line graph. A line graph in which time is always on the horizontal scale and the variable you're measuring is always on the vertical scale. So looking at problem 16 here. Most people are aware that life expectancy, the number of years a person can expect to live, is much longer now than it was, say, a century ago. Here are the numbers for women provided by the National Center of Health Statistics. So we have the year, we have the life expectancy of females. We can see that it has been increasing since 1900 up through the year 2000. We want to construct a time plot of this data. So what are we measuring here? Well, we're measuring life expectancy. What's the units? Years. Along the bottom is always going to be time for a time plot, which we're talking about the year as well. Years 1900. 1910, 20, 30, 40, 50, 60, 70, 80, 90, up through the year 2000. Up the side, well, if we look at our life expectancies from about 48 years up to 80, and again, we want to spread that out as much as we can. Pick something that's easy to use. Let's go by 5-year increments. Do we need anything between 0 and 45? No. So what you can do is do a squiggly line down here that shows you're compressing those first 45 years. So then we're going to start here at 45 and go up from there. 50, 55, 60, 65, 70, 75, 80, and we don't need to go any higher than that. Now our time plot, we're simply going to take and put dots up above each one. So in 1900, 48.3. Whoops, wrong spot there. That's 1910. We want to go to 1900. 51.8. 54.6. 61.6. 65.2. 71.1. 73.1. 74.7. 77.5. 78.8, and 79.5. Connect those with a segments. There's your time plot. Okay, so there's a summary of things that we have talked about throughout this section. If you have questions on those things, make sure that you would be getting those answered before you hand in the homework and take the quiz, and more importantly, the chapter test. All right, I want to go back to this example here and show you how you can do the histograms on a graphing calculator. So what I want to do first is I'm going to put this data into our calculator. The way that you do that is you hit your stat key and edit. That will allow you to edit any list you want. Now I've already put the data in here, but I do want to show you how to clear out lists as well. I don't want to clear this list. Obviously there is nothing in list 2, so I'm just going to enter one thing in there and show you how to clear a list. Go up and highlight the list number you want to clear. And this you have to be very careful with, because if you just hit delete, it's going to delete the entire column and you'll no longer have a list 2. Once you have the list highlighted you want to clear out, hit the clear button and then hit the down arrow. That will clear out the entire list. So once you have that data set entered in to your calculator, go ahead and exit out of that menu. Hit second function and the y equals to get into your stat plot menu. Hit enter on plot 1. Make sure plot 1 is turned on. And you see you have 6 different graph types that you can do. You can do a dot plot. You can do a line graph. You can do a histogram, a modified box plot, a box plot, or something that we'll get into later, which we're not even going to talk about now because that'll come when we talk about regression. So I want to go over and I want to highlight the histogram, hit enter. It's going to ask you what list you want to pull from. We want to pull from list 1. From there, hit your zoom key, and depending on the calculator and what software it is running, you want to hit zoom stat. On this calculator up here, that's zoom and number 9. When I do that, there is a picture of our histogram. As you hit the trace key and you go along the histogram here, you see that it has chosen the class intervals for you. Minimum value is 78, going up to 134.2. Tells you that there are 6 data points that fell within that range. Next class width, 134.2 to 190.4, tells you that 8 data points fell in there. Well, when we did our histogram by hand, if we move ahead to that, okay, remember we selected class widths of 50. So let's go ahead and go into our window of the calculator and let's put in the class widths that we are looking for. We want to go from 51 up to, biggest one is 40, so actually let's go from 50 to 40, or 400. That includes all of our data points then. Remember our data points, in this section went from a low of 78 to a high of 359, so that should include everything. Now our X scale is what's going to set our class width. We went by 50, so let's go ahead and set that at 50, hit enter, and now graph again, and it should look a lot more like the histogram that we produced. Now when we hit trace and we go along here, it tells us that we are going from 50 up to 100. Actually, let me change that. We went from 51 on ours, so let's change that to 51. Now when I hit trace, it goes from 51 to less than 101, which is the same as less than or equal to 100, which is what our class widths were. 3 in that class width. In the next category, 101 up to and including 150 or less than 151, n equals 7. 5 in that class width, none in this one, 2 in that one, none in that one, and one in that one. So you can use your calculator to better organize the data so you don't have to necessarily go through and make tally charts. Okay, if you were asked to do this on a quiz or a test, go ahead and put the data set in your calculator, choose what you want for the class intervals, and now you don't necessarily need to hand frequency all of them, because once you complete this, you could go back now and in our first category, put 3 tally marks. The next one put 7. The next one put 5. Next one 0. Next one 2. Next one 0. And next one 1. So use the graphing calculator capabilities to the best of your ability to help simplify some of the graph making techniques.